Alright, so stress in chapter 9 shouldn't be confused with your everyday stress, or in this case, in the physics world, it means the change in length of a stretched object depends not only on applied force, but its length and cross sectional area. So the formula below is the force, not the force in Star Wars, divided by the area, or F over A. It is used to measure many things and objects in this case.
One type of stress is tensile stress, which is the applied force per cross sectional area. Basically, it is a state of stress that causes an object to expand or stretch. So, for example, I have a rubber band, and if you put weight on it, which I have a ring, the weight causes the band to expand due to the stress that it's putting on it. You can determine how much the rubber band stretches by using Young's modulus. If you are given the mass, length, area, and y for rubber, you can solve for delta x. Delta x gives you the change in length due to tensile stress on the rubber band.
Compressive stress is the pressure on an object when a force such as weight is being applied to it. For example, if I put this Coke can on top of this one, the force from the top Coke can would cause the bottom Coke can to compress and therefore decrease in height. Using the example of the Coke cans, we can find how much stress the bottom can is under. Stress equals force over area. And given that each can weighs 0.87 pounds and has a 1h radius, we can find stress by dividing the weight of the can divided by the area. This comes out to be 0.28 pounds. We can determine that the bottom can is under 0.28 pounds of stress.
The third kind of stress is called shear stress. Shear stress is caused by equal and opposite forces acting parallel to the cross-sections of an object's material. Shear stress also tends to deform an object. Take, for example, this book. The book is composed of many pieces of paper stacked on top of each other. These are the cross-sections of the book. I'm going to apply a force across the top of the book parallel to these cross-sections. The table exerts an equal and opposite force on the book. As you can see, the book is deformed as it is exposed to this shear stress. All objects are slightly deformed by shear stress, even if it is difficult to see. The concept of shear stress is very important in engineering. Take, for example, this pillar. If the material the pillar is made of has a small shear strength, the pillar will not be able to withstand a large amount of shear stress. If this person and this cat exert equal and opposite forces on opposite faces of this pillar, the pillar could bring down the roof above them.